Good day and welcome back. Today we're going to talk about the mutual inductance, which is the last topic in electromagnetic induction. At the end of this video, you should be able to explain the phenomenon of mutual inductance and also derive its expression. So the phenomenon of the mutual inductance is something similar as the self-inductance, except now it involves two coils. Usually, we will name these two coils or solenoid as the primary coil and the secondary coil. We have learned that when there is current flow in the primary coil, there will be magnetic field produced and it will link to the secondary coil. If we change the current in the primary coil, such as we adjust the value of the resistance, this also changes the magnetic field that link to the secondary coil. And according to the Faraday's law, there will be an induced EMF in the secondary coil. In short, mutual inductance is a phenomenon in which an EMF is induced in a coil when there is change in current in a neighboring coil. Besides changing the value of the resistance, we also have seen a similar case, which is the transformer. The transformer uses an AC current where the magnitude of the current is changing all the time. The AC current will produce a changing magnetic field, which will induce an EMF in the secondary coil. Now let us study one example from the past questions in 2018. You are given with two circular coils X and Y, and the mutual inductance between the two coils is 2 Henry. From the diagram, we can see that the current is flowing from the positive terminal of the battery to the coil, and it will be flowing in a clockwise directions from our view. From the questions, the current in X is decreasing at a constant rate from 5 ampere to 0 in 10 seconds. So from this statement, we can calculate the rate of change of current, and then we can calculate the induced EMF in Y. The formula of the induced EMF is given as negative of mutual inductance multiplied the rate of change of the current. Put in all the value and you will obtain the induced EMF in Y is equal to 1 volt. To calculate the induced current, we can just apply the formula of the V equal to IR, and you can see that there is 2 ohm resistor in the secondary circuit. Put in all the value and you will get the value of the induced current equal to 0.5 ampere. Now, there is one more thing that we need to identify is the directions of the induced current. So the current in X is decreasing. Based on Lenz's law, there will be an induced EMF in Y to prevent the decay of the current. To do this, the current in Y must flow in the same direction as in X, so it will be also a clockwise direction in this case. However, take note that the question asks for the directions as observed by the P. So the answer of this question would be B, since the direction of the induced current seen by P is an anti-clockwise direction. Now we're going to derive the mutual inductance between two coaxial solenoid of the same cross-sectional area. The setup of these two solenoid is something look like in this picture. You can see that the center of both these solenoid are aligned and both of them are having the same cross-sectional area. So you are given with the formula of the induced EMF equal to negative M multiplied rate of change of current. And from the Faraday's law, we also learned that induced EMF is equal to negative of rate of change of magnetic flux. The following steps of the derivations is quite similar as the derivations of the self-inductance. First, we equate both the expression and we will get Mi equal to V. So we have learned that the flux is equal to NBA, where the N is the number of turns of the secondary coil, while B is the flux density produced by the primary coil. So we also have learned that the magnetic flux density in the middle of the solenoid is given as mu naught Ni. Substitute in the formula. In the end, you will get the formula of the mutual inductance as shown in the slide. So now let us try one more question from past year in 2019. You are given with the number of turns of both coil P and Q, and also the length and the cross-sectional area of coil P. Based on the diagram, you can see that coil Q is tightly wound around coil P. You can assume that the area of coil Q is the same as the cross-sectional area of coil P. Now the current in P is decreasing uniformly from 12 ampere to 0 in 58 milliseconds. From the discussion, we have the equations of induced EMF equal to negative mutual inductance multiplied rate of change of current. With this setting, we can substitute in the formula that we have derived, put in all the value, and you will get induced EMF in coil Q is 4.04 millivolt. Before we end the session, let us compare the self-inductance and the mutual inductance. Both of these inductance are the phenomenon of the induced EMF in the conductor due to the change in magnetic flux linkage. They obey the Faraday's law and Lenz's law, and they have the same unit as Henry. The difference between self-inductance and the mutual inductance is the factor that causes the change in magnetic flux. For the self-inductance, the change in magnetic flux is due to the current flow in the coil itself, while in mutual inductance, it is caused by the change in current flow in a neighboring coil. The formula of the induced EMF and the derivations of the inductance for both these phenomena are quite similar. So the formula of the induced EMF and the inductance are summarized as in the table. So that's all for my discussion today. If you have any questions, you can leave it in the comment section below. Also, do leave a like and subscribe my channel. I'll see you in my next video. Thank you.